Hey guys, so I'm just going to go over some brief network statistics and in particular some of them that relate to Gephi. So first, look at the simple stuff. So the most simple things you could look at over a network are the number of edges and the number of nodes. So of course these are a very basic description. Beyond that, Gephi also provides a couple other very basic descriptions. These are in the statistics panel on the right hand side. So one of these is the connected components, and it's just a count of the number of separate groups of nodes. So a group of nodes are considered connected if there's a link between them. So a single node with no edges would be out there as its own component. Another thing to look at is the graph density. So this shows up as the the percentage of possible links that are present. So given that there are, here we count 6 nodes in the network, we count 10 possible edges. And of course, this is not the fully connected network. So these are some basic stuff that you can get at. Looking in a little more in depth, you can run the average degree calculation. And so what this will do is it'll show you a graph of the degree distribution. It'll also show you the in degree and out degree distribution. This gives you a lot of information on the network and is definitely one of the first things you should look at. You see it'll give you the average and it'll fill that in. It'll also give you the distribution. So comparing to some classic networks, a pure random network, which would be an Erdős-Rényi network, where you just throw down a bunch of nodes and randomly draw edges between them, is going to end up with a Poisson degree distribution. So that's what you see drawn here. And a preferential attachment network, this would be something like the Barabasi-Albert model, where you put down a bunch of nodes, right, and you connect 2 nodes, but with a probability where it's more likely to connect to a node that has a higher degree. And so you end up with is a few nodes have much higher degree. And so this ends up being a power law degree distribution described by the power law exponent gamma. So the degree distribution is proportional to k to the minus gamma. And you can see here we've got the power law, which will show up as a straight line on a log-log axis with slope minus gamma. One of the other simple things you can run through is the path length. So here we've got kind of the same network, and the path between node I and j is going to be denoted as dij. You can get at all of these things by running the average path length module. It'll give you the average path length, and it'll also give you the network diameter, which is the maximum path length. So it's going to go ahead and compute this, which will be, you could think about storing this as a sparse matrix, or actually it might be, in this case, it would be a full matrix, right, of all the possible path lengths between, right, and you're going to look at the shortest path lengths. One other thing you can get out of this is, and I think these will also, you'll get from running that same module, in the statistics panel, you also get the betweenness centrality. So this is the number of shortest paths across a particular node. So given that you've computed all the shortest paths from node I to node j, you can imagine a little guy or girl running across the network and running across each shortest path. And if they drop a package at each node they visit, the betweenness centrality is going to be the number of packages that each node ends up with. So you think of this kind of an accumulation. There's a couple other things you could look at. The degree centrality, which you've already talked about. That's the degree of the node. So a high degree node is going to be more central in a degree centrality measure. Another thing is the edge centrality. So a lot of network algorithms work well by considering edges rather than nodes, and a lot of statistics as well. That one's not in Gephi. Stuff is mostly node focused. 2 others that you'll get are the eigenvector centrality. So given that A is the adjacency matrix of the network, where, so it's a matrix with every node I and node j as the rows and columns, and if it's unweighted, there could be 1s or 0s. 1 where there's a connection between node I and j, and 0 where there's not. It could also be weighted, so you have 0s and the weights. And to find the eigenvector centrality, you go ahead and compute the eigenvector decomposition. So here you'll select the largest eigenvalue, lambda, and for each node, the entry in that corresponding eigenvector, x, is going to be the eigenvector centrality of that node. There's another measure too where this is the closest or the closeness. So the closeness metric across the whole network, you're going to be considering the inverse of the shortest path between every two nodes. So you want to know, okay, given a node, how close is it to the rest of the network? So you can consider the distance to all the other nodes in the network and run that sum across the whole network. Some more centrality, classic algorithm called PageRank, which is actually the algorithm that Google originally used to sort web pages, is like eigenvector centrality in that you can state it as a eigenvalue decomposition, and you can also here it's written as an iterative algorithm. You can also see this as an eigenvalue problem, which is how it's computed in practice. But here, you assume a uniform distribution of the page rank across nodes, and then you update it. So if there are, you update each node's page rank by considering the page rank of nodes that point to it. So here you sum the previous page rank with a learning coefficient d, usually around 0.85 if you read on the algorithm, and you have a penalty L for the distance between two nodes. So this I don't think it's how they compute pages now, how they compute the rank of pages now, but it was interesting because it relied on people, because it relied on the links between pages which people were constructing. Another thing to look at is clustering. So there's two different ways to compute clustering. Gephi computes them a second way, which is a global measure. The first measure is the Watts and Strogatz measure. So this is from one of their original papers, and here you're considering the average over the whole network of a locally computed quantity. So right next to clustering, we've got an example network, and for the C1 coefficient, you're considering each possible, each node. So there's 4 nodes in the network. We've got 4 sub networks here, and you're considering the number of connections between neighbors. So here for node 1, we have a 0, right? Neighbor B isn't connected to anyone. Node 1, node B, you have 1/3. So 1/3 of the possible links between its neighbors exist, and so forth. So you take each of these individual C1 values, C1A, C1B, C1C, C1D, and you average them for the C1 coefficients. You average each of those across the whole network. Here you'd get 7/12. The way that Gephi computes this, and I think is probably a slightly more intuitive way, is you go across the whole network, count up the number of triangles in the network. So you can see here for this network, we have 1 triangle, the BCD triangle, right? And then you count all possible triples, right? So we're going to go ahead and count that there's 5 different triples given the edges in the network. So of those, we have 1/5 of the triples that are closed. So it's a number, and to calculate this, we're going to multiply the triangles by 3, because there could be 3 different ways to draw this triple. And finally, this exists as an algorithm in Gephi, and is a pretty active area of research, is network modularity and structure detection. This particular network is NCAA football teams, and you can see pretty clearly running this modularity algorithm, they were able to detect the individual conferences. This is from a Closet paper, who is one of the lead researchers in this area in 2008. That's all we have for networks. Thanks for listening, and that's pretty much what you can check out in the Gephi panel. You can use these to inform your visualization and learn about the network.